Correct. So now we're going to go and solve this problem the way the textbook solves it, at least with a number of elements, and we're going to use 2 elements to solve this problem. Okay, so I spoke briefly about the ways to improve the accuracy of a finite element solution, and formally, the one that we're doing now is called H refinement, so we're using more elements. Okay, so what we are doing is more of the same type of elements. So we had quadratic elements that we did in the single elements example, and now we're just going to use 2 quadratic elements. And that way, the approximation of that element, that quadratic field, with the linear strains and the linear stresses, are going to be over smaller domains. So it's going to, that way, it's going to be more accurate. Okay, so we don't have to approximate over the entire structure, but only a small part. And the smaller we make that part, the more sensible a quadratic element is to approximate that. And that rationale is really based on the Taylor series expansion. As you know, that if I have a Taylor series expansion around a point, so a small domain, then essentially a linear or a quadratic approximation is highly accurate. It's almost exactly if I move small amounts away from that point. And that's really what drives the logic behind H refinement. Alternative is to say, let's do P refinement, and that is, let's do polynomial refinement, making the order of the polynomial higher. So if we had started with a linear element, and then say, okay, the linear element is essentially a linear displacement, constant strain, constant stress over that. That's way too inaccurate. Let's rather go for a higher order element, and then boom, go for a P refinement strategy. So typically what we do in finite elements is we go with P refinement as high as quadratic elements, and that's where we stop typically. Some researchers or some people will go higher. That's called Trex elements, and there's lots of fancy names for those elements. But the point is we'll always stop at quadratic elements. And as a matter of fact, in this course, if you're unsure what to do, use a quadratic element. That's the bottom line of what this is why I only do quadratic elements in classes and focus on that so highly, because that's your go-to element if you're not sure what to do. Okay, so that is typically what P refinement. Once we get to that quadratic elements, then we typically make sure we do H refinement from there onwards. Okay. Another topic of refinement that's not well known and not actually well discussed in finite element books often, it's what's called R refinement. And what we do here is we use the same number of elements, okay, but we don't have them equal size. So we don't have a uniform measure of them. So we might have some of the elements describing a large part of the domain, some describing a smaller part of the domain, depending on where the polynomials where the field, the displacement field, is varying a lot. So we have sort of a constant displacement field, then we can have one element, one simple element there, as a matter of fact. But when the displacement field is going up and down, and some crazy oscillations and stuff like that, then we need to have lots of elements there. And then we rather than have lots of small elements in that domain to try and capture that behavior. So that's really what's called R refinement. And this is quite also another way of thinking about solving the problem, to say I'm using the same number of elements, I'm using the same or type of elements, I'm just using them optimally, I'm just using them sensibly. So this essentially becomes an optimization problem, where to put the nodes, how to do the mesh. So this is really where you optimize the mesh, but without not changing the number of elements and nodes in that mesh. Okay, so that's really what R refinement is. But that's enough said. That will give you a good overview of refinement strategies in finite elements. Now we can go and say, let's get rolling on what's going on with the 2 elements. Okay, first off, we need to number these elements. Okay, so what I'm just going to do is I'm going to number the elements 1 to 5. So number the nodes from 1 to 5. So I'm going to put a node down at point 1, 2, 3, 4, 5. This is the same as the textbook. So that's essentially what we do. Then I can know essentially that element 1, the local numbering for that element, remember, was always the left-hand side node, the right-hand side node, and the mid-side node. So if I ask myself, so this is the left-hand side node here, so that is node 1, maps to 1. I'm just putting in the global coordinates elements numbers here so I can keep track of them. Then I'm saying this was always the node 2 in that local element numbering was always the right-hand side node, so that is the right-hand side node, is node number 3, that's why I'm putting 3 there. And then the mid-side node was always this third number in that local system, and now that is essentially the mid-side node is number 2 in the global system. That's why I have a 2 there at the end. And if I follow the same logic for this element, I would say essentially I have a 3 for the left-hand side, 5 for the right-hand side, 4 for the mid-side. Okay, so that's where this element numbers come. So this is now keeping track of my global node numbers related back to my local node numbers. Okay, so this is really, if you forget about this, this is left, right, middle node in that local numbering. We always have this 1, 2, and 3 in that local numbering. Okay, now I'm putting down my coordinates. So I'm putting down where I'm putting those mesh points, or those nodes at least, at x1, 0, x2, 10.5, x3, 21, x4, 31.5, and x5, 42. So I'm just doing a nice uniform mesh. That's beautiful. Okay, so the mid-side nodes are always in the middle. Okay, so that's essentially what we have there. Let's make sure that is the case. 10.5. Yeah, okay. So that's what we see here. And all of those are nicely in the middle. So then what I have is I have the area, all these things written out. Okay, so that's good. A and A's, and these things are all constants. Then what I can do is I'm showing you now how to compute the consistent node of those, the stiffness matrices using that form in the textbook. So this is also important that you understand if E and A are constants, and the mid-side nodes are in the middle, and then we can use those closed form expressions for computing the stiffness matrices, so that's appropriate. Okay, the textbook simplification of the body forces as a constant, I'm doing that simplification now. So what we are doing in this case is I'm solving exactly the prescribed textbook example. Okay, so I'm doing a simplification that we will normally not do. Just making that loud and clear. But this is essentially what you see is I'm showing you how to compute that if you wanted to use, if you do that simplification and you wanted to use that form in the textbook for the consistent node loads that they've already integrated for you, for your convenience. Okay, and now I can go and say my global stiffness matrix is essentially a 5x5 matrix, and now I need to say, where do I need to assemble? I need to now assemble this local stiffness matrix K1 and this local stiffness matrix K2 that I've constructed with the local node number 1, 2, and 3. But I know that relates to the global node numbers via, where is that? Via this element list. I need to go and assemble things in the right place. Okay, so what I'm going to do is I'm going to go loop over my elements, okay, for element 0. So this elements list has got the first element as the first row and the second element as the second row. So I'm looking at the first row of elements, and I'm saying I will loop over the entries there, and J will also loop over the entries there. And then what I can say is let's assemble this in the K global, and the relationship between these numbers here, 1 to 5, and the position in K, because K's index starts at 0, the K indexes will run from 0 to 4. So from 0 to 4, where the numbers run from 1 to 5. So that's why I subtract 1 in here every time. But I send in the K global and say, take this global position and this global position, okay, and assemble it in the right index in K. And that's what I'm doing. And I'm saying K global is equal to K global plus something. I'm not just overriding K global by saying it's equal to just K1 n by n comma n or something. I'm putting it in the right place. Okay, so that is important to understand. Okay, and what all of these n's and m's are is just we're running over the columns 1, 2, 3, and 1, 2, 3 over the rows 1, 2, 3, 1, 2, 3, and the columns 1, 2, 3 of this local stiffness matrix. So remember, this n here just runs from 0 to 2 indexes and 0 to 2 indexes. And we know that essentially the first column is associated to what is the entry that's stored in the first column of this row vector. The second entry in this local is associated with what is the second column in this row vector. Third entry here is associated with the third column in this row vector. That's why we just have these two variables n and m that just runs over this K local with the variables there. Okay, and we're making sure that we're putting it in the right places by looking at which is the associated global coordinate for that local index. Well, that's essentially what we're doing there. And then I'm just making sure as we go through this loop, I increment n by 1 and I increment n by 1. Okay, and here I'm just resetting every time I'm just resetting for each row. We're going to run over the columns. Next row we're going to run over the columns. Next row we're going to run over the columns. And this is just to reset the columns index, the m equals to 0. Okay, and then I can print the K global after I've assembled one element, and then I can say let's do the second element, and the second element that I do is by saying elements 1 and elements 1. So the second row of this. So that's now the second row. So those are the indexes for the second element, and then I just repeat this process and assemble the K global stiffness matrix. Okay, that is what we have there, and then I can do the same for the F global in terms of the force. So this is now the first one we're going to look at how to do the assembly of the force, but it works the same way. It's a little bit simpler because our forces just run over the indexes of this element, first element, and of the second element. Okay, and again, I just have a local index for my force indexes from 0 to 2, and same here from 0 to 2 for that local force description. Okay, so that's what this F1 is, my local force description. It's got indexes 0, 1, 2, but I need to figure out where to put them in the right place in the global, and that's given by I running over the columns of the row vectors for elements, for the first element, and there's the row vector for the second element. And then again, F global is equal to F global plus Fni. Okay, that is important. We are assembling. That is that assemble process, not just overriding what was there. So that's now, once we've done it, we've assembled this, and then we could go through the similar process of just essentially solving this system. Let's just see what the time is. In my parent service is 10 minutes. So I'm going to complete this, and then we'll look at the results now. So then I can solve for the unknown displacements. Yeah. So that is essentially I'm just constructing the, I'm solving, so here I'm solving the reduced system and making sure I'm putting over that column of the stiffness matrix that multiplies by the prefab displacement, so I adjust my force vector, and then I can assemble my displacement, full displacement vector. That is important. Okay, so it's the 0 plus the unknowns that I've just computed. And then after that I can go through the same process of, again, essentially computing U1 and U2. But now what I'm going to do is I'm going to plot them essentially over x1 and the x2 domain for element 1 and for element 2. So I'm not going to just plot them over psi minus 1 and 1, because otherwise I'll plot them over each other. Because both of these elements run from psi in the local domain from psi minus 1 to 1. I'm now making sure I'm plotting for element 1 and for element 2. I'm plotting in the x domain. So this is what you'll see. That's different in the plotting here than what we had before. I'm now plotting plotting these displacements in the x domain. So although I'm still running with psi from minus 1 to 1, I'm then getting the right x's out and the right x's for the second element out by doing this. Okay, so that is important that we have by just making a numerical expression of my isoparametric formulation. Because here I'm setting up isoparametric for the element 1 and isoparametric for the element 2. Okay, so that's that. Then we can plot displacement, we can plot strain, we can plot stress, and then we can see how things look. So if I look at this, then I can see my displacement looks like this. This looks already a lot better than the single element. If I look at this, I can already see a much better strain approximation, still under predicting everywhere. Stress versus exact also everywhere, but quite a much more accurate kind of solution than what we've had before. Okay, so this you can see, this is now solving it exactly the same way as what they solved in the previous experiment. I would like you, I'm not going to do this, but I would like you to make a copy of this notebook and solve this, not with the constant, but with the linearly varying body force for the two elements, and compare those solutions, and then interpret that critically. All right, thanks. This is sort of our first encounter of the two elements, and now you see what are the steps involved. Is that we're just assembling the K global, and we're assembling the load vectors properly into the system. Where's the load vectors? We're just assembling that properly. And this is exactly the same as the textbook. So if something is not clear yet, please first go to the textbook, go through the example. It's very well explained and self-explanatory. Make sure you can go, we've done everything in the course so that you can really easily follow what's going on there. And if you can't follow easily what's going on, please make sure you join the session at the Blackboard Ultra to ask questions. Okay, hopefully this was clear and give you a good idea of where we're heading.